So hello again. Tonight we're going to talk about whether the consensus is that there's other planets or dwarf planets in our solar system or not. And there's two camps, and we'll get into that. So as usual, I watch lots of videos on a subject before I present on it, whether or not there might be other undiscovered planets or dwarf planets in our solar system, be they numbered 9, 10, or whatever. There's a computer simulation that's fairly popular with the Find Other Planets crowd, and they believe there should be one, not multiple, just one, and it should be about Neptune's size, which is about 8 times the size of the Earth. And then there is the AI-assisted scanning of archived observations, and they say that there should be one larger than the Earth, smaller than Neptune, and they've actually unconfirmed observed one in imagery that's separated by 23 years. The problem is that the computer simulation says that this thing should be bigger and in a particular location. And this AI-assisted scanning of archived observations says it's a little larger than Earth, but smaller than Neptune, and it's in a slightly different location. So these two analyses disagree with each other. And I watched another video where it said, if we do find one and it's smaller than Earth, it would rule out the possibility of there being any others to be discovered. And I find that conclusion a bit suspect. Throughout human history, whenever somebody or a group says, we know exactly how many of these there are, or we found them all and there can't be any more, they're quite often wrong. The number of stars in the Milky Way has gone from millions to billions to soon to be hundreds of billions. The number of exoplanets in the galaxy went from, no, it's only Earth that's a planet, to many thousands. I think it's closing on 6,000 now. Not all of those are Earth-like, but I think the number that are Earth-like are in the 30s. They're close approximations of Earth. The number of galaxies in the universe. In the 1920s, we thought of Andromeda as a nebula, not as another galaxy. And from that point in time, we progressed to from one galaxy, meaning our own, to millions of galaxies. And now the number of galaxies are billions. There are debris fields in the solar system, probably familiar with the asteroid belt. There's another one farther out, kind of in the Pluto area, called the Kuiper belt. And then much farther out, instead of it being a flat disk belt, there's actually a spherical cloud of small bodies called the Oort cloud. It's predicted, but we haven't found a lot of objects from there. But what we have found is a lot of long-term comets seem to loop around out into that part of the solar system and then come back into the inner part of the solar system, I don't know, every 70 plus years, kind of like Comet Halley. They're so small and so far away. They're not like in another star system. They're not light years away. They're just billions of astronomical miles away, hundreds of astronomical units to thousands of astronomical units. And until we observe them and calculate their orbits, we can say they maybe exist, or under computer simulations they exist, but without actually observing them and getting them confirmed, who knows how many are out there. So the solar system is large. It extends out to about 110 astronomical units. An astronomical unit is the distance from the Earth to the sun, 93 million or so miles. So 93 million times 110 is kind of like the diameter of the heliosphere, solar wind affecting area around our solar system. But we haven't looked everywhere within that spherical space. We've looked wherever it was convenient. So some things, some areas may yet to be observed ever. There's also, we put out a particular kind of instrument, either on Earth in space, and the minimum diameter of the detail is sufficient for, like, we're looking for distant galaxies or we're looking for distant stars, but there's not enough detail in the resolution to see something much smaller. I one time exchanged an email with somebody who was doing an infrared survey, and he was looking for particular objects outside of our solar system. And I asked him in an email, can we see some of these Oort cloud or Kuiper belt objects? And he had to point out that they're too small for the pixel resolution of the infrared instrument they're using, because they're looking for big things like stars and galaxies. And even though they're farther away, they're bigger. And the other thing is, as we look to the outer edge of the solar system, particularly from our observations of Pluto, we find that a lot of them have carbon on the surface of them, which reduces their albedo, their brightness as reflection from the sun, which means if we're looking for a certain visual brightness, it may be far dimmer than that. If we're looking for a certain infrared brightness, it may actually be sending out much less heat than that. And so it's there. It's not so tiny we can't see it. It's so cold and not reflective enough that we can't see it, even though it's sitting right there. And also the computer simulations, absent sufficient baseline observational data, they can't calculate the disk or spherical orbits. And so when they go to do a simulation, the simulation may not point out how many things might be there because they don't have enough observations in the simulation. And as to how big something is or how bright it will be, those are just presumptions. And, we presume that it'll be big enough and reflective enough of the sunlight that we'll be able to pick it up with our wonderful, James Webb Space Telescope. If it's not that reflective and not that bright, even the JWST can't pick it up. Even though JWST can pick up galaxies that are, about 14 billion light years away, those are big. So they've taken to scanning of historical archives of images and other data, and they're saying, well, this is far too much for humans to do. So they've used artificial intelligence assistance tools to train it to look for certain things and then go and look. And that's how this 23 years apart and two different infrared space-based telescopes have found this object, because it was so small that it was otherwise filtered out. We were looking for something else like stars. Who knew we could find a little tiny, planet-like object? And if it's low enough and the pixel resolution is small enough, can you really call it a found dwarf planet if it's just 4 pixels, or is that noise? And also, if we're looking out into space, you can't look near the sun or the moon or point back if you're out at L2 at Earth or at bright galaxies or nebulas, because if you're looking for incident light, like reflected light, these things are way too bright and they'll blot out the area, because that's how we're looking at things, is either the light they produce or the light they reflect. And where we can observe in the sky changes throughout the year. So if we're looking, let's say, out from L2, away from the Earth, away from the sun, and we're on one side of the orbit of the Earth around the sun, we can't look behind us. That part of the sky is off limits, because you don't want the James Webb Space Telescope facing back towards the sun, because it will damage it. So that part of the year, it can only look in that part of space. And also, we're part of the Milky Way galaxy, which has a lot of stars in the core of it. And we can't look towards the galactic plane because there's so many stars there and so much brightness. Also, the central bulge, where there's like a higher density portion of stars, that can't look there either. And the cosmic microwave background, when they went to observe that, not in the first or second set of observations, but in the third set, they took a picture, had this glorious picture, and they had the disk of the Milky Way right in the center of it. And people were saying, like, the disk of the Milky Way is not part of the cosmic microwave background. So they had to go through a follow-up pass of the existing data to subtract out all of the brightness in microwave of the central disk and bulge. And now you had just the cosmic microwave background without this giant galaxy sitting there. So you have to, know what you're looking at, through, and to. So when it comes to scanning archives to look for things that we didn't find before, earlier infrared telescopes were not as sensitive as the contemporary technology. And also, early infrared telescopes were not as, let's say, helium cooled as the current ones, so they can't look into the far infrared or well into the medium infrared. They could only look in the near infrared. So if it was even dimmer in its glow, couldn't even see it. The earlier instruments were either on Earth or they were in Earth orbit, not out at L2 like the James Webb Space Telescope. So they didn't have the dark enough skies. And also, we've developed these things called adaptive optics, where if you shine a yellowish looking laser on the bottom side of the atmosphere, the heat turbulence of the atmosphere can be detected by measuring the light travel time, and then you can negate that in your observations and correct for the dimpling of the atmosphere to make the image much, much sharper. And therefore, you can see things that might be small or dim where we couldn't see that before. And when you're talking about a survey telescope, even the Gaia survey telescope could not see the entire sky because it's out at L2 and Earth gets in the way. They'll show you the picture that Gaia took of the sky, and you'll see these black, like blotted out areas, and that's where it couldn't look. So it can't look in certain places. So when they talk about a survey, it's not a complete survey of the entire sky, it's where they can look. And also, if you have a survey that's looking for galaxies like Gaia, the closer things get in the way and they know to avoid them. So if Gaia is staring off at a particular galaxy or area and they're doing a stripe and it happens to run across Jupiter or Saturn in the image, they just black that out, subtract it out because they know where it's going to be in the sky. But thankfully, the more recent archives have kept in them the things that were basically rejects. So if something was deemed too dim or too fuzzy or too near the galactic plane or bulge in prior astronomical observations, that would just be junk data thrown away. But somebody got smart and said, it's just data. It doesn't take that much to store it. It's not like the recording tape reuse of the videotape used for the moon landings that they overwrote. We can afford to, store more digital data nowadays. So they keep all of the things that were not in the end results. Also, calibration or test images. Occasionally, if they get an anomalous reading off of an instrument or a camera and a pixel, they'll go back and say, okay, let's shut down official science observing, and then they'll do calibration or testing of the underlying sensors, and that's just testing data. It's not like they're really looking for something, but nowadays they keep the test and calibration data as part of the archive. They don't wind up in the reject pile. But earlier missions, it's just test data. Throw it away afterwards. Otherwise, it takes up space. Well, we've gotten smarter, and if you're looking for galaxies, you might want to find stars later on, or maybe use AI to find them for you. So things that we used to just toss away as, well, that wasn't part of the mission plan, is now actually kept for future missions. So I think we need to think about how we look for things in the solar system. We'd like to look out to about 2000 AU, and the light travel time one way is about 278 hours or 11.6 days approximately. In other words, if we were to emit some kind of signal, be it a radio signal or a laser, and we want to see, if anything bounces off all the way out to 2000 astronomical units, we would send the signal out and continue our sending of the signal. And then we'll get back to that part, 11.6 days later and see if anything reflected in the meantime. So stop relying upon reflection and emission from these objects, invisible or infrared light, and start relying upon, we're going to send the signal out from Earth. And then we're going to give it time up to about 11.6 days. And if we see something in the meantime, we'll look at the signal that comes back and see if the data we encoded in the signal is actually still in the signal. So it's kind of like when the law enforcement officer gets you for speeding using a radar gun. The radar gun isn't just a light beam kind of radar gun. It actually has data saying, here's the serial number of the radar gun, here's the last time it was calibrated, and here's the data that we got back, so that the radar beam that bounced off the front of your car actually bounced off the front of your car, because they know where the radar gun was pointed. Same sort of thing here. If we have a radar beam or laser, if we have a radar beam that sources from the Earth, then we can put into the beam data that when we get a reflection signal back, we know exactly when that signal was sent out from where as part of our striping of the sky. If we were to use a small array of large diameter radio telescopes in orbit of the Earth beyond geostationary, it would mean that the array goes around the Earth slower than the Earth rotates. So we can actually have the array look at a particular part of the sky for more than 24 hours. So it can gather data for a long period of time before orbit marches on and it looks at a different part of the sky. And with the right separation and size of radio antennas, we can get to a fraction of an arc second of space pointing, beam diameter. And that should allow us to look out to about 2000 AU, well out beyond the Kuiper belt into like the inner portion of the Oort cloud. And we don't have to worry about, facing the sun or moon or bright planets because we know where they are and we can subtract them out. But at that distance, we might be able to detect things that are out in the Kuiper or the Oort that we can't even detect with our best infrared or optical telescopes. Something else is providing the light, either the sun reflection or heat from the object. In this case, we're bringing our own flashlight. Things that are obvious will be near to us. Things that are much farther away, stars, galaxies, or nebulas, would not return a radar reflection within the expected time frame. So we could actually find a dwarf planet in the Kuiper belt if it was right in front of the Andromeda galaxy, because the object in the Kuiper belt would reflect the radar in a timely fashion. The radar beam going beyond the solar system, we could care less about how long it's going to take to get to Andromeda and back. So it's kind of like if you're looking in your camera focuser and you've got a chain link fence between you and what you're trying to shoot, you can adjust the focus and pick up the chain link fence, and all the other stuff in the background will just be blurred out. Same sort of thing. The beneficial side of this is not only will we be able to detect dwarf planets, other planets, all the way out to the edge of the solar system, but we'd also detect the closer in things that we haven't seen yet. More asteroids, more comets, maybe more moons of Jupiter and Saturn. And given that it's radar based, if we find a near Earth object or a potentially hazardous object, we could use this much like we used to use the Arecibo giant radio dish in Puerto Rico as a radar unit. So we could actually do radar imaging of a particular target if we found that there was something there. So what would be good? Let's see how small a thing we can detect. Voyager 1 and Voyager 2, I looked up the information on them last night, and Voyager 1 is currently at 167 AU. Voyager 2 is at 140 AU. And then I've got the billions of kilometers and billions of miles, and the one-way light travel time, hours, minutes, seconds. So we know where they are because we communicate with them via radio on a regular basis. If we have a deep space network that can pick these up with a 70 millimeter single telescope, it's picking up something that's coming from the 12-foot diameter parabolic reflector antenna on Voyager 1 and on Voyager 2. So we could send a signal out that far, it would reflect off the reflector and come back to Earth some number of days later. We just don't want to use a radio signal that's around 8.4 gigahertz because that's what the Voyagers use, and we don't want to burn out their transmitter. If we had an array of about maybe 50 meter flower petal opening in space kind of things at larger than geostationary orbit, we would have a synthetic aperture of about 1,000 feet, about 5,000 feet, because we would have them individually separated by 1,000 feet. So we would have the biggest somewhat permanent radio telescope array for the human species to be able to detect this stuff. So we should be able to pick up these two tiny objects even at that distance because we're sending out an encoded radio signal and we're expecting it to bounce back in a day or so. So that would prove that we can do it. That would prove we can pick up very small things, and we could avoid looking at other things that we already know where they're at. But we could also find new moons around planets. But here's the funny part. Given that the accuracy would be sub-arc second, we could actually detect things that go behind and come out from behind other planets in the solar system. So if you're looking for something that's out in the Kuiper belt, right now you would not be able to observe it within the slightly larger than the diameter of Uranus and Neptune, because it would disappear behind them. And that area of obstruction would be larger than the planet itself because its atmosphere extends out. Well, same thing is true in this case, but we're shooting a radar signal, and the radar signal, if we choose the right frequency, could go right through that atmosphere and then come off the dwarf planet at distance and back to us. So this would be, as I call it, the ultimate solar system survey project. And we're only looking for things in the solar system. We know where the things are that we found before, and we should be able to find lots of new things without going, there won't be any more, or there's lots of more. We, observe. So in summary, stop claiming that in our solar system there should be other planets or dwarf planets. Stop claiming that there should be no other ones. Actually make a definitive effort to observe and confirm them. Space is big. There's lots of room for unobserved stuff to be found. And all the predictions in history about quantities of stars, galaxies, and exoplanets have always been so way off. Continue spending on finding asteroids and comets that might jeopardize Earth. This could be kind of a project in that regard. The side benefit is that its archives would allow you to scan for planets. Don't discard things that are test or calibration images simply because they're not part of your mission parameters. If you're looking for galaxies, doesn't mean that in your image you might not have a dwarf planet. And you never know what you're going to find until you actually make the effort to look for it. So you have to create the technology and use it to create the observations that you're going to need to find things. Do move to radar, not infrared, not visible, and do put some technology up there at greater than geosynchronous, and create a synthetic radio telescope array. How big the individual telescopes are and how many of them are and how far apart they are, that's up for somebody else to decide. But I just think it's a final way of saying, yep, we did scan the entire solar system and this is what we found. Look at all the new stuff we found, or unlikely, but didn't find anything else. So that was all the different videos that I looked into as to, is there not? How did we? And then what is this Kuiper belt and Oort cloud, and where are Voyager 1 and 2 now? And how do we communicate with them with this thing called the Deep Space Network? And then I have that actual report out on the search for Planet 9 using 2 infrared surveys 23 years apart. And then for those people that want to actually just look at the archive data, and it's more than just the pictures, it's actually the digital raw data from all these observations. The Space Telescope Science Institute, STScI, they have the McCoskey Astronomical Space Telescope Archive, the MAST archive. It has the James Webb Space Telescope, Hubble, Kepler, Gaia, and all these other ones, including the ones that were kind of indirected, the Pan stars and the SDSS. There's multiple generations of those. And then if you want to know about what was this IRSA thing, and what was the Akari project, and you mentioned Gaia, what's Gaia? And then you also mentioned that we ought to look at the archive data from Sophia, because it was infrared as well, and it might have found things, but if that's not what they were looking for at the time, then that data just sits in the archive waiting for somebody to spot it. Okay, so did it give people any insight that there might be other things out there?
Probably pretty sure probably is.
Yes.
Just from the probability.
Yes. It's like somebody was doing a completely unrelated YouTube video when I was watching it, and somebody said, it's kind of like in your bathroom sink, you see one ant, and you go, well, there's only one ant. Right. Where are all the other ants? They don't come by one. Well, if you find one dwarf planet out there and you go, well, we found them all now because we found one. If we took that attitude, Clyde Tombaugh would have never observed Pluto because it just looks like a little dim star. So any thoughts regarding let's put a radio telescope array in Earth orbit out beyond geosynchronous? What
You
is
know,
out beyond geosynchronous? Well, first of all, you're beyond all of the cable TV satellites that are out there at geosynchronous. You're beyond all the weather satellites, so you won't get in their way. The reason why they put them at geosynchronous is you put them in orbit above a particular location on the Earth, and they're orbiting the Earth as fast as the Earth turns. So they stay in the sky. That's why when you go, why are all the direct TV satellites receivers pointed in exactly the same direction? Because that's where the satellite is for our latitude. You go further north, the antenna changes. But this would be moving slower than the Earth rotates. So they would stay pointing at a particular part of the sky for a longer period of time. Okay, I said it was going to be a short one. Any comments or questions before I stop recording?
there's a train of thought that we're looking at things that are very far away, out of our reach. I wonder what's the reason, what's the purpose, what's the value of just to look and see things that are zillions of miles away. We could
Well, at one time, Christopher Columbus tried to convince the royalty, I know it's zillions of miles away and nobody's ever been there before, but I think there's something over there. Same sort of thing.
But he could reach it. He could reach it. We can't reach these things that are that far. We might be able to see it.
Oh, no. He was just very lucky that he got there. There were a lot of attempts to make it to the New World that you never heard from again. But you don't hear much about them because you never heard from them again. So easily reached? No. If you look at some of the trips from Europe to the New World that got caught in the Gulf Stream of Florida and wound up, I don't know, at a place like, St. Augustine, Florida. They didn't intend to land there. That's where they landed because they got caught in the Gulf Stream and headed north.
I thought they were looking for trade things like the spices or something.
They were. They knew that China's that way, and they said, well, if the Earth is really a globe, really a round sphere, we ought to be able to go over this way, and it might be closer. They had no clue.
Worth a try.
And that's what they said. Hey, king and queen, why don't you give me some money? I'll go buy some ships. I'll drag some crew members on board, and we'll head out that way and see what we find. And hopefully we'll come back. Same sort of thing. The human species has the desire to explore and see the unknown. And nowadays it just costs a lot of money to create the technology to do it. But the nifty thing about this would be that we're not attempting to go light years to another star system. We're just attempting to look and see what's there in our solar system just farther out. Remember, using our antiquated propulsion technology, it took 10 years for the New Horizons probe to get from Earth to Pluto. It's easier and cheaper to send radio signals, and they'll only take, a couple of days because they're moving it close to the speed of light.
Once we invent the beamer machine, it'll help us,
Well, given Arecibo's demise, they've actually been using one of the dishes in the Deep Space Network in California to act as a radar receiver to be able to do radar imaging of near-Earth asteroids. So when we spot something that's moving through the sky fast enough, we go, let's calculate the orbit because it could be headed for Earth in the future. So they'll plot the orbit using regular telescopes. And then if they want to see it up close and see, okay, how big is it? What shape is it? Kind of how much mass it's got. Has it got anything orbiting it? What are the details? Is it a rubble pile or is it rock? They'll do radar imaging of it. And with Arecibo gone, they could no longer do that. So they paid basically a branch of the SETI radio telescope array out in California to be the transmitter. And they use the Deep Space Network dish in California, one of them, to be the receiver. And now, once again, they can do radar imaging of potentially hazardous things headed our way. So this would be like an extension. Instead of looking for just one object because we know where it is and we've already calculated its orbit, we would be looking for anything that's out there. But it would be in our solar system. Okay, I'm going to stop recording.